Rust's ownership system is built on 3 ironclad rules. Rule 1. Every value in Rust has exactly one owner, a single variable that holds the responsibility for it. Rule 2. When you assign that variable to another, ownership moves and the original is invalidated. Rule 3. The ampersand operator creates a borrow, a non-owning reference that lets another part of your code look at the value without taking it. To see why these rules matter, look at how Rust lays out a string in memory. A string is stored as 2 parts. A small piece on the stack holding a pointer, a length and a capacity, and a separate block of data sitting out on the heap where the actual characters live. The stack portion points to the heap portion, and only that pointer arrangement is what your variable owns. When ownership moves, only the stack part moves. The pointer, length, and capacity get copied into the new variable. The heap data itself stays exactly where it is. The compiler then nukes the original variable, so there is no chance of 2 variables pointing at the same heap allocation, and both trying to free it. That is how Rust eliminates double free bugs at compile time, with 0 runtime cost. The borrow checker is the compiler component that enforces these rules. Try writing 2 mutable references to the same value. The compiler refuses to compile. One mutable borrower, or many immutable borrowers, never both. This is the rule that catches data races before your program ever runs. Think of it like a library book. There is exactly one copy of the book on the shelf. If you check it out to mark it up with a pen, a mutable borrow, you are the only reader allowed to have it. Nobody else can even look at it while you are editing. The librarian will not hand out any other reference to that book until you return it. But if you only want to read the book, an immutable borrow, the librarian is happy to hand out many copies of the reference at once. A dozen silent readers can all look at the same page simultaneously. Reading does not change anything, so there is no conflict between them. Here is the critical constraint. You cannot mix the two. As long as any immutable borrower is still reading, the librarian will not let a mutable borrower edit. And while one person is editing, no one else is allowed to read either. This combination rule is what eliminates data races, because data races require one writer and one reader touching the same memory at the same time, and Rust forbids exactly that pattern. That is the whole ownership model in one picture. One owner at a time, moves transfer responsibility without copying data, the ampersand borrows without taking, and the borrow checker enforces a strict library policy that no compiler before Rust could enforce at compile time. No garbage collector, no runtime overhead, no data races, just rules the compiler checks before your code ever ships. Rust's ownership rules prevent you from using a value after it has been moved. This demo shows a compile error from a move, then a clean build using a borrow instead. First we create a Rust source file that triggers a move error. The value s is assigned to t, which moves ownership away from s, and then the code tries to use s again. Compiling this file produces a classic E0382 borrow check error. S was moved to t, and is no longer available. This is Rust enforcing ownership at compile time, not at runtime. Now we write a second file that uses a borrow instead of a move. The ampersand makes t a reference to s, so ownership stays with s, and the original binding remains valid. Compiling this version succeeds with no errors. The borrow checker is satisfied because t only references s, and the print statement uses the still valid original binding. Every program eventually has to clean up after itself, and how it does that defines the language. Java, Python, and Go ship a garbage collector that chases live objects at runtime, reclaiming what you forget. The cost is real. The collector stops the world to scan, burns extra memory for bookkeeping, and you never write a single free. C and C++ reject the collector and hand you the keys. Malloc and free, new and delete. It is blisteringly fast, but with no safety net. Forget a free and you leak. Free twice and you double free. Use a buffer after its lifetime ends, and you get use after free, the classic doorway into CVs and exploits. Rust splits the difference with a move. Assignment transfers ownership, so the old binding is invalidated and only one name owns the data. The compiler enforces this through the borrow checker before your code ever runs. No collector, no manual free, zero runtime overhead. Before a value gets moved, the compiler asks a simple question. Can this type be duplicated by copying its raw bits? That is what the copy trait declares. Primitive types like i32, bool, char, and f64 implement copy, so assigning them copies the bits and the original binding stays valid. Look at this snippet. Let x equals 5, let y equals x. Both x and y are usable here because 5 is in i32 and i32 is copy. The compiler does not invalidate x, it duplicates the bits into y. A larger type like string is not copy, so assigning it would move ownership and kill the original binding. Here is the payoff. Rust guarantees memory safety at compile time with no garbage collector and no manual free. You get the speed of a system's language and the safety of a managed one. And the borrowing rules plus the copy trait are exactly how that promise is delivered.